Yes, we're going to talk about graph problems and algorithms for solving graph problems. First, we're going to recall the notions used to describe graphs and the different types of graphs, such as directed and undirected, weighted, unweighted, cyclic, acyclic, trees, connected, planar, many different kinds of graphs, regular graphs. And then we're going to start talking about first problems, computational problems involving graphs such as shortest path, single source shortest path, all pair shortest path, and algorithms that solve these problems. And we're going to talk about more involved problems, minimum spanning tree problems, and algorithms solving the minimum spanning tree problem, such as Prim's algorithm, Kruskal algorithm. And we're going to proceed to maximum flow problems. So minimization problems, maximization problems, optimization problems. We're going to discuss Ford-Fulkerson, Edmonds-Karp algorithm. And we're going to talk about bipartite matching and algorithm for computing a maximum weighted bipartite matching. Well, to be fair, we're not going to cover the famous Floyd algorithm here. And finally, we're going to close with discussing the minimum cut problem and its relation to maximum flow. So that's our plan. So let's recall a little bit types and notions of graph. So graph consists of vertices and edges between vertices. And we usually denote with n the number of vertices and with m the number of edges. And here you see some example graph. It has many nodes and it has vertices and it has many edges. And this graph, as you can see, for example, is disconnected. It consists of three components, right? So, the slide, yes, here. This is a one component, and this is one connected component, and the rest is one connected component, but there's no way of getting from here to this component to this component, or from this component to this component. So components, and also this is an example of an undirected graph, namely the edges here in this drawing don't have arrows, meaning that one can go from here to here as well as from here to here. And there were two ways of capturing that mathematically. One by having two edges, one directed edge from here to here and another directed edge from here to here. So that means an undirected graph can be considered as a special kind of a directed graph where each edge is accompanied with the edge in the opposite direction. And the other perspective is that undirected graphs are a category, a type of their own, where there's no even talking about a direction of the edges at all. And that's just basically two ways of capturing that mathematically. So mathematically, a directed edge or a ZF directed edge is a subset of the Cartesian product of the vertices with themselves, so that each directed edge is a pair of two vertices with the understanding that the first vertex is the start vertex and the second vertex is the target vertex. And if we have, if this set of edges is directed, if to every edge in one direction, there's also an edge in the opposite direction, then we speak of undirected edges. But as I said, this is basically misuse of notation, undirected edge meaning here that there are two directed edges in opposite directions. So far we've had talked about the case of unweighted graphs. But for some later applications we'll talk about weights being assigned to edges. So a weight function in this sense is mapping from the edges to, let's say, the natural numbers. So we prohibit negative weights here. And for simplicity, we also prohibit non-integer weights like fractions or transcendental numbers. But sometimes our algorithms will be able to generalize and cover also that case. So, and in this perspective, it is possible that an edge in one direction can have a different weight from the edge in the opposite direction, even if the underlying graph is undirected, right? Undirected, recall, means there are two edges in one direction and in the other, but the way the weight function is defined here, it is very well feasible that the edge in the one direction can have a weight different from the edge in the opposite direction. And if we want also the edge weight to observe, to obey symmetry C, then yeah, we're going to say that. Sometimes we're going to include special values for the weights. So 0 is already included here in the natural numbers, right? We're computer scientists after all. And sometimes we will also allow the special value infinite, which is a synonym for larger than any of the other edges, right? So since the set of edges is always finite, that means any edge weight function will have a maximum value, and it makes no difference usually for graph and graph problems if we say an edge has weight infinity or an edge has weight larger than all other finitely many edges have weight. We can actually, so a total graph, let me talk about a total complete graph. Complete graph is a graph where every possible edge is present, and we can capture a non-complete graph as a complete graph where the edge weights indicate whether the edge is present or absent. Let me say that again. We can artificially turn a non-complete graph, like in this picture, this is not a complete graph. This edge is missing, for example. We can turn that into a complete graph and recover the original non-complete graph by considering edge weights to have values 0 and 1 to indicate as an indicator function whether the original edge was present or not. So, and here's the way of encoding a graph with weighted edges, namely as an adjacency matrix with possibly non-zero weights. So adjacency matrix has entry 0 and 1. It's a matrix whose vertices are yeah, are the numbers labeled the rows and the columns. So the rows of the matrix are labeled with vertices, the columns of the matrix are labeled with vertices, and the entry at the matrix with indices ij corresponding to vertex I and vertex j is 0 if the edge is absent, and is 1 if the edge is present, and is 17 if the edge has weight 17, and so on. So we can, in this way, represent both unweighted and weighted graphs as adjacency matrices. We can represent both directed and undirected graphs as asymmetric or symmetric matrices. Symmetric adjacency matrix corresponds to an undirected graph. Yeah, symmetric edge relation corresponds to symmetric adjacency matrix, and non-symmetric adjacency matrix corresponds to a directed graph. And some types of graphs are whether the graph is simple or not. So we usually focus on simple graphs, but sometimes we can also treat non-simple graphs. So non-simple graph is a graph where there may be multi-edges, where there may be edges between two vertices, several edges, several ways of going from one vertex to the other and back. And also non-simple simple graphs don't have loops. So usually we don't include an edge from a vertex back to itself. There's no need to do so, but sometimes we will consider also such graphs with loops. And so a simple graph is a graph without loops and without multi-edges. Another important graph concept is about the degree of a vertex. So if we have a symmetric graph, an undirected graph, then the degree of a vertex counts simply the number of edges that are adjacent to that vertex. However, if we have directed graph with directed edges, then we need to distinguish between the in degree and the out degree, the number of incoming edges and the number of outgoing edges. And in simple but important combinatorial observation is the so-called Handshaking Lemma, which says that the total number of incoming edges of a graph, not of a vertex, but of a graph. So let's count all incoming edges for all vertices, that this must be the same as the total number of outgoing vertices of all vertices. So for each vertex, we count how many edges are outgoing, and then we add this for all vertices of the graph. And the two numbers must be equal because they both simply count in different ways, in different orders, but what they both count is simply the total number of edges. In the first case, we simply count and assign to each edge the target vertex of that edge, right? Every edge has a unique target vertex, and the in degree of the target vertex counts the number of edges that go into that vertex, and every edge goes into precisely one vertex. So that's one way of simply counting all edges. And the other is another way of also counting the same cardinality of the same set, the number of edges, namely every edge is leaving some vertex. So counting that gives the same number, and that's the number of edges in a directed graph. That's in combinatorics, this is a simplest principle of so-called double counting, and this what we see here is a simple instance of that. It's called the so-called Handshaking Lemma, and one consequence of that is, since let's consider an undirected graph, right? Undirected graph. Then the statement says, or a consequence of the statement is that every undirected graph has a vertex of even degree. Okay, we'll return to that later. So, right, so now we've been talking about degree, in degree, and out degree. A regular graph, let me also say that, a regular graph is a graph where every vertex has the same in and out degree. So here's, for example, this component is a regular graph, a two regular graph, because every vertex has two adjacent edges, right? But here, for example, this lower component is not regular because this vertex has three edges and this vertex has only one edge. So different number of edges for different vertices, that's not a regular graph, and this is a regular graph. Also talk about directed and undirected paths. So yeah, a path is a sequence of edges intuitively, right? So for example, here's a path that starts here, goes here, then here. That's an example of a path. A sequence of edges that are adjacent to each other, that stepwise share the destination and source vertex for the next step. Let me refrain from making this overly unnecessarily formal. You have a clear idea what a path is. And if the underlying graph is directed, then we need to talk about directed paths. which respect the direction of the edge in which we traverse it. If the underlying graph is undirected, then we can traverse the edges in any way as we like. And right, let's talk about connectedness. So two vertices are connected if there's a path from one vertex to the other. That may be a directed path in case we have a directed graph, or it might be an undirected path in case we're talking about an undirected graph. So, and the component is the largest connected subset of vertices. Let me say that again. So two vertices, no, let me say it in with order. Vertex T is connected to vertex S if there's a path from S to T that respects the orientation. And a set of vertices is connected if there's a path between any two of the two vertices. And the connected component is the largest subset of connected vertices. And so, yeah, intuitively, we've already seen the connected components of this graph here, but let's verify that formally. So these four vertices, any two of them are connected. For example, these two vertices are connected. There's a path from this vertex to this vertex for sure. And so you can verify formally that any two vertices in this of these four vertices are indeed connected. So it's a connected set, and it's the largest connected set. We cannot add any other vertex from this graph because no other vertex or adding any other vertex would violate the connectedness of this component. So yeah, to conclude, this is a connected component of an undirected graph. If we talk about directed graphs, as things start to become a little bit more subtle, and here we need to talk about strongly connected components. Strongly connected components in a directed graph is again a subset of vertices, such that between any two pairs of vertices, there's a directed path. In particular, there must be a path from S to T and the path from T to S, possibly a different path. It's an important subtlety. Might well be that the path from T to S uses different intermediate vertices than the path from S to T. So that's a strongly connected component in a directed graph. A subgraph is simply a graph which uses a subset of the vertices and the subset of the edges. And an induced subgraph is one that only uses a subset of the vertices and all edges that are connected to this subset of the vertices. So that's an induced subgraph. And since we talked about adjacency matrix, notice recall that the adjacency matrix is a square matrix. So the square matrix, yeah, we can multiply two square matrices to get another square matrix, right? And in particular, we can square a square matrix. So, and if we square the adjacency matrix, this gives rise to another matrix, and we can interpret it, that other matrix again as the adjacency matrix of a graph. So yeah, we can go back and forth between weighted graphs and adjacency matrices. We can turn a given weighted graph into an adjacency matrix, and we can square that adjacency matrix if we like, and then convert that squared adjacency matrix back into a graph. And this is called the square of the original graph. Yeah, so we kind of borrow and transform the terminology from matrices back to graphs. So the square of a graph is the graph whose adjacency matrix is the square of the adjacency matrix of the original graph. And similarly, we can talk about the cube of a graph. That's a graph that corresponds to the cube of the adjacency matrix, and so on for arbitrary powers. And considering powers of graphs and powers of adjacency matrices will become relevant and helpful later when we talk about connectivity algorithms and connectivity properties. Right, so here are some special kinds of graphs. Yeah, there are many graphs, different graphs, some with few edges, some with many edges. But the graphs that you see here on this slide will become helpful and will occur later frequently. So it makes sense to introduce and recall them separately, and to also introduce notation for these graphs. So what you see on the bottom line are the complete graphs. Remember, complete graph is a graph that has edges between any two vertices. So here K3 has 3 vertices, K4 has 4 vertices, K5 has 5 vertices, K6 has, and so on, right? And being complete graph means that all possible edges are present. All edges that can be drawn between any two vertices are actually present, like here or here or here. And the number of edges is, of course, yeah, the binomial. So Kn, the complete graph of n vertices, has n times n plus 1 over 2 many edges. All as many edges are possible as many edges as there are pairs, unordered pairs of vertices, right? It's an unordered graph. That's important to emphasize. The complete graphs are undirected graphs. Another family of interesting graphs are the cycles. So here you see a cycle on 3 vertices, a cycle on 4, a cycle on 5, cycle on 6. So you get the idea, right? So a cycle just starts on one vertex, and then visits the other vertices in any order, and to return to the original vertex. So these are all connected vertices, and of course the 3 cycle is the same as a complete graph on 3 vertices. Then we have a family of graphs that are called cubes and hypercube graph. So the name comes from these 2 pictures. The cube graph is a graph on 4 vertices, remember square basically. Yeah, let me emphasize that's an important thing. The way we draw a graph may be different, so we can draw the same graph in different ways. So it's important to distinguish between a graph itself and the drawing of a graph. So we can draw the same graph, this C, for example, and pull the vertex, let's say this vertex here, and move it around, or move that vertex around. As long as the edges follow, this will still always be the same graph, just different ways of drawing that graph. Yeah, and that being said, let's now talk about the hypercube graphs. So this is a 3-dimensional cube graph where the vertices are, for all for drawing purposes, arranged as the vertices of an actual geometric cube, and then there are edges whenever there's an edge in the geometric cube. And you can imagine also the 4-dimensional hypercube graph, 5-dimensional hypercube graph, and so on. A formal way of specifying the hypercube graph is in dimension d. Consider all bit strings of length d. So for example, here we have all bit strings of length 3. This is a d-dimensional hypercube. So all bit strings of length 3 are a way of labeling the vertices of that hypercube graph. And an edge formally exists between any 2 vertices, between any 2 bit strings of length d, if the 2 bit strings differ in precisely 1 bit. Let me say that again. If 2 bit strings, all bit strings have length d, if 2 bit strings length bit strings differ in exactly 1 bit, then there's an edge between these two vertices represented by this bit string. Let's verify that here. So for example, here these two vertices are labeled 001 and 011, and you see they differ in precisely 1 bit named the middle bit. The first and the last bit are the same, and only the middle bit flips. So, and same here for these two. These two vertices are labeled 001 and 101. So the labels, the bit strings differ in the very first bit, and the other two bits are the same. So since they differ in precisely 1 bit, there is an edge, and this is the edge. So that's a formal mathematical way of capturing the Hypercube graph, family of graphs. Here we have the complete bipartite graph. The graph is bipartite if the vertices can be partitioned into two groups. And here you see already the drawing in such a way to reflect these groups, right? So here's one group and here's another group. And a complete bipartite graph is one, well, let me first say what a bipartite graph is. Where the vertices can be partitioned into these two groups, and where any edge is actually running between different groups. So no edge within a group. That's important and defining condition. So for example, this edge is prohibited because that would be an edge in this group. And similarly, this edge is prohibited because it would be an edge within this group. What is permitted are edges between different groups like this and this. And the complete bipartite graph is one where any edge is present that is permitted according to this rule. Any edge that connects between vertices in different groups is present. So this is a complete bipartite graph of order 2, 3, 2 vertices in one group, 3 vertices in the other group. This is a complete bipartite graph of order 3, 3, 3 vertices in one group, 3 vertices in the other, and any possible edge that that leaves a group is present. And so on. This is complete bipartite graph of order 3, 5, complete bipartite graph of order 2, 6, and so on. The final class of graphs that we're considering here for later reference is the graph of are the grid graphs. So here you see a grid graph of order 4, 4. So they're the vertices of the grid graph are, as the name suggests, drawn in this setting on a grid of size 4 times 4. So they are 16 vertices, and there's a edge between any two vertices that are share the same position on the grid. That's you get the idea of a grid graph. Good, so now we've seen many example families, not just single graphs, but family of graphs parameterized. So the complete graphs are parameterized by the number of vertices, 1 parameter. The cycle graphs are parameterized by the number of vertices as well, 1 parameter. The hypercube graphs are parameterized by the dimension, so that's 1 parameter. The complete bipartite graphs are parameterized with 2 parameters, size of the first group, size of the second group. And the grid graphs are parameterized by the size of the grid in one direction and in the other, and maybe they are higher dimension than their additional magnitudes to consider. Let's now talk about some properties of these graphs. We already talked about connectivity, and you can see that the complete graphs are all connected, right? And so are the cyclic graphs, and so are the hypercube graphs. All these graphs are connected. So that's one property easy to check. Also, they are all undirected graph as drawn here. One can consider them also as directed graphs let's say, with having these edges directed one way from up to down, let's say, or a cycle graph having the edges oriented in a circular manner. It's not so immediate at how to orient the edges in the complete graphs, but anyway, then let's talk a little bit about the degree of these graphs. So what is the degree of the cycle graphs? So here every vertex has two edges, every vertex has two edges, every vertex has two edges. So the cycle graphs are all two regular, right? So every vertex has two edges. That means it's regular. All vertex have the same degree, in degree, out degree. And this in degree, out degree is 2. So it's two regular graphs. How about the complete graph? So these are also regular graphs. Every vertex has the same degree. Here the degree is 2, here the degree is 3, here the degree is 4, here the degree is 5. And generally, the complete graph on n vertices has degree n-1. One less, yeah, because we don't have self loops. There's no edge that starts and ends in the vertex itself. But they're all edges present to all other n-1 vertices, so therefore every vertex has degree n-1. So it's a regular graph. All vertices have the same degree. Same here for the complete bipartite graph. All vertices in one group have the same degree. All vertices in another group has another degree, possibly another, but they all have the same degree. And same for the grid graph. Well, not same for the grid graph because they are internal vertices, they are boundary vertices, and they are corner vertices. And they have different number of edges, and therefore this is not a regular graph. What properties about graph are we interested in? Diameter. Diameter is, well, let's first talk about the distance between two vertices. Okay, let's suppose we have a connected graph. That means there is a path from between any two vertices. And the length of the shortest path, this is called the distance between the two vertices. We say that again. We consider two vertices. Suppose that they are connected, that there is a path, and the length of the shortest path, that's the definition of the distance between the two vertices. If we have edge weights, then it's the distance is the sum of the least sum of the weights of the edges from the south vertex to the end vertex. Let me again say that. If we have weighted graphs, then the weight of an edge contributes to the distance. And when we talk about the shortest path, and when we mean the shortest weighted path, whereas in general, we mean the shortest path just charging the same cost to every edge and not considering weights. And so, yeah, and the diameter is the largest distance between any two vertices. So put differently, the diameter of the graph is the maximum of the distance, and the distance between two vertices itself is the minimum length of a path, so that the diameter is the maximum of a minimum. Maximum of minimum is the diameter. Maximum of distance, and distance is the minimum length of a path, max min. Let's calculate the diameter for some of these graphs, shall we? So let's calculate the diameter of the complete graph. This complete graph K2 has obviously diameter 1. The largest distance between any two vertices is 1. Same here. This complete graph has also distance 1, a diameter 1, and this one as well. Between any two vertices, there's an edge, by the definition of being a complete graph. So we can get from any vertex to any vertex using just one step. That is beneficial in many applications to have graphs with small diameter. For example, if we consider routing problems, if we want to transfer data from one vertex to the other, then we can do that directly from start vertex to target vertex by following the edge. However, if the graph is not complete, then we may, like for example in the cycle graph, to get from here to here, we need to take all this long detour, which is quite expensive and involved, right? So it's a much longer way. We cannot take one edge directly. Instead, we have to go all the way around. So yeah, that means that the diameter of the cycle graph is larger than 1 in general. It's actually n over 2 rounded down if it's n is odd. So for example, here n is 5, and the diameter, the largest distance between any two vertices is 2. We can get from here to here using this path, using only 2 edges. This is shorter than taking this path. And this is the worst case. So the diameter of the cycle graph of length of size n is n over 2 rounded down if n is odd. And so we see here benefit of the complete graph over the cycle graphs, but there's also a disadvantage, namely the degree, right? So the complete graph has very short diameter, as small as it can get, diameter 1, but it has very large degree, namely it has degree n-1, so the degree grows linearly asymptotically, whereas for the cycle graph, the degree is constant, it's 2, it does not depend, it does not grow with n. On the other hand, the diameter is growing linearly. So that these two graphs they are all connected, but there's exhibit the kind of extremes of a trade-off between diameter and degree. Small diameter and large degree for the complete graph, and large diameter and small degree for the cycle graph. And for the Hypercube graph, we similarly see here the transition. This is kind of an intermediate case. So let's calculate the diameter and the degree of the Hypercube graph, shall we? So first the degree, let's take some evidence from empirical evidence. So the degree of any vertex here is 2. The degree of any vertex here is 3, which suggests that the degree of the d-dimensional hypercube graph is actually d. And I'll leave it to you to formally confirm that. Recall our definition of the edges, mathematical definition of the edges of a hypercube graph. Okay, hypercube graph of dimension d has degree d, so it's a regular graph. Every vertex has the same degree d. So that's one thing. Let's express the degree in terms of the number of vertices. How about that? Right. So we have here expressed the degree in terms of the number of vertices and seen that it's constant. We have expressed the degree here of the complete graph in terms of the number n of vertices and seen that it is linear. And here, how many vertices does a hypercube graph of dimension d have? Hypercube graph of dimension d has 2 to the d vertices, right? Every vertex is represented by a bit string of length d. So there are 2 to the d many bit strings of such length, and therefore there are 2 to the d many vertices. So 2 to the d vertices, n is 2 to the d. And now let's compare that with the degree, regular graph of degree d. So that, all vertices have the same degree d. Now express that in terms of the number of vertices. Since the number of vertices is 2 to the d, that conversely means that d is the binary logarithm of the number of vertices n, and that's also the degree. So let me repeat that. The degree of the hypercube graph as regular graphs is logarithmic in the number of vertices, because the number of vertices grows exponentially in the dimension which agrees with the degree. So the degree of the hypercube graph grows logarithmically in the number of vertices, which is much better than the linear growth exhibited by the complete graph. Right? We call that the complete graph has degree linear in the number of vertices, and here it's only logarithmic. On the other hand, logarithmic is still worse than the constant degree of the cycle graphs. 2 is a constant, right? So that these hypercube graphs, in a sense, are really kind of an intermediate case, an interpolation between the two extremes, the cycle graphs and the complete graphs. They are also intermediates in terms of the diameter. Recall that the diameter of the complete graph is 1, constant. The diameter of the cycle graph is n over 2, linear. And the diameter of the hypercube graph, let's look at that. What's the worst case? Which are the furthest vertices in the hypercube graph? The furthest vertices are from one corner to the opposite corner, right? From the vertex that has all bits in a certain way to the vertex that has all bits flipped. It doesn't matter which vertices we take, but it's really about flipping all vertices. This will result in two vertices having the largest possible distance in the hypercube graph. And what is that distance? Well, the distance is the dimension -1. No, the dimension. Let me say that again. The distance between any two vertices in the hypercube graph is less or equal to the dimension, and the diameter, the largest possible distance, is equal to the dimension. Because, why is that formally so? Well, the picture already suggests that empirically, but formally the reason is that we take one edge to change one bit, another edge to change another bit, and another edge to change the next bit. And we continue that process until we've flipped all possible bits. And then we're really at the opposite vertex. The furthest possible vertex is the furthest vertex. And still it's reachable within d many edges, steps, d many steps. And now let's again rephrase that d, that this is the logarithm of the number of vertices, so that the diameter of the hypercube graph is logarithmic in the number of vertices, so that also in this sense here, we have a kind of intermediate and interpolation between the two extremes exhibited by this graph. So here, this graph has constant degree, but linear diameter. This graph has constant diameter, but linear degree. And the hypercube graph has logarithmic diameter and logarithmic degree. So that's a kind of trade-off between both cases. And these different graphs are actually used, for example, in parallel computing, so-called transputers, but that's another topic, not the topic of this lecture. Okay, so let's also investigate the diameter of the complete binary graph. So the diameter of the complete binary graph is also 1, is 2 actually, yes, is 2. If we have two vertices, if they're in different groups, then there, by the very definition, there already is an edge. And if the two vertices are in the same group, then we must take a kind of detour, first switch the group, and then return to the original group. And let's also talk about the grid graph. So this is a two-dimensional grid. The diameter here, let's first talk about the size of the two-dimensional grid graph. So when we have size m in one direction and m in the other direction, then the number of vertices is m squared, right? Or put differently, the diameter is the square root, twice the square root of the number of vertices, twice, because first we traverse here and then we traverse here. So now we've determined the diameter and the degree of all these graphs, and we've seen that there's a trade-off between diameter and degree. And then finally, last point of discussion for this slide is about planarity. The graph is planar if it can be drawn in the plane without edges crossing. So this is a exception to the rule that I mentioned before, that we don't really care about how a graph is drawn. Here we do care whether the graph is drawn with crossing edges or without. For example, here these three graphs are drawn without crossing edges, but here is an edge crossing, here are edges crossing, and here are edges crossing. And with edge crossing means that visually they overlap, but it's not possible to transfer from one edge to the other. So here there seems to be a crossing, but imagine this to be subways, then it's not possible to transfer from one subway here to the other subway line. So it's only in the drawing that these edges seem to meet, whereas as graphs, they don't really meet these two edges. And that's a bad thing, right? From the perspective of perception and visualization, it suggests that two edges meet where in fact they don't. So we want to avoid that in a field called graph drawing. These graphs here are all crossing free. There's no crossing here. Here the question is a little bit more subtle, because we can draw the same graph in a different way without edges crossing. That's an important thing. Let me emphasize that again. A graph may be planar. Planar means it can be drawn without edges crossing, but that same graph can be also drawn with edges crossing, in which case it still is planar, because planar does not mean how it is drawn, but how it can be drawn. For example, K4 is the complete graph with 4 vertices. The way it is drawn here, we see that these two edges are crossing, but it's also possible to draw the same graph without edges crossing. You can easily see how to do that. So that means K4 is actually planar, although it is not drawn in a planar way on this picture. K5 cannot be drawn in a planar way. It must have crossing edges. Again, please do the effort and try to draw it. Don't take my word for it. Try it yourself. Try to draw K4 without edges crossing, and try to draw K5 without edges crossing. Succeed in the first case and fail in the second case. That's an important lesson. So these are all planar graphs because they can and are drawn in the plane. These are non-planar graphs. These cannot be drawn in the plane without edges crossing, like K5. This is the smallest bipartite graph that cannot be drawn in the plane without edges crossing. Whereas the grid graph obviously is a planar graph. It is drawn in the edge without edges crossing. So to summarize this slide, what we've seen here, what we've learned is actually a lot, right? We've learned about many different kinds of graphs. We've learned about properties, quantitative properties of graph, like the degree for regular graph, the maximum degree if the graph is not regular, the diameter, short diameter is good, low degree is good, but we cannot have both usually. So there's a trade-off between graphs that have small diameter and large degree, and graphs that have a large diameter and small degree, and some intermediate graph families. And the final property we've discussed here is whether a graph is planar, meaning whether it can be drawn in the plane without edges crossing. Not whether it is drawn, but whether it can be drawn. Okay, and now we take a short break, and then we continue with graph problems. And this is time for and your opportunity for asking questions in the chat. Okay. Yes, thank you. There's a great, several great questions. Correcting an earlier mistake of mine, I erroneously claimed that K23 is not planar, cannot be drawn in the plane without crossing. And this was a lie. This was wrong. K23 can be drawn. Here, the way it is drawn is with crossing. There are many crossings, but it is possible to draw that also without crossings by kind of moving some of the lines like rubber bands. Imagine that edges are like rubber bands between vertices. The vertices are fixed in the plane like pins in a desk, and the edges are rubber bands between these pins. And then indeed here, these are the shortest drawings, the shortest, like rubber bands, but we can pull the rubber band in such a way that they don't intersect, that there is no crossing, so that K23, the complete bipartite graph with 2 and 3 vertices, indeed is a planar graph because it can be drawn without crossing. Thank you. That's a very good and important observation that allowed me to clarify and emphasize again the difference between between a planar drawing of a graph and the graph being itself being planar. And K33, this is the smallest bipartite graph which is not planar, which cannot be drawn in the plane without edges crossing, where it is really truly unavoidable and not just a matter of how I drew it, but fundamentally internally impossible. Then there was a great question about how to check whether a graph is planar. This is indeed, again, a very important question, also algorithmically, and we will address that later in chapter 5. So please be patient and bear with me because it really involves some very nice classical combinatorics to get an efficient algorithm for checking whether the graph is planar or not. Because the naive approach, as you can imagine, the manual approach is a very unreliable. It's not an algorithm, it's a heuristic. The manual approach is just to try to pull the edges, rubber bands in such a way that they don't intersect anymore in this pulling process. This pulling process is what, there's no rules about how to pull and when to succeed and when to give up. So that's not an algorithm in any rigorous sense, but indeed we will devise an algorithm that will be based on very interesting and nice combinatorics. Right, then there's a question about the diameter. Right. the diameter, let me say that again, so the distance between two vertices, the distance between two vertices is the length of the shortest path. Okay, and the shortest path, of course, will not pass through a vertex more than one time. A path can pass through the same vertex several times, but if we're considering shortest path, then there's no reason for doing so, right? If a path passes through the same vertex several times, then we can shortcut that part, right? Where it kind of cycles through that vertex. And thus, by shortcutting, we arrive at a shorter path. Therefore, a shortest path will never meet this, visit the same vertex repeatedly. Thank you very much for asking that question. That's a great question, great opportunity for clarifying that. So let me say it again. A shortest path will not visit any vertex repeatedly. In general, a path can visit a vertex repeatedly. Then it's not a simple path. A so-called simple path visits 8 vertex at most once. And shortest paths are always simple paths. They never visit a vertex repeatedly. And therefore, the diameter is also only concerned and involved with shortest path. So when counting the diameter, that means the largest distance between any two vertices, but the distance considers only shortest path, and therefore does not pass through vertex repeatedly. Thank you. Okay, so that concludes this slide. And now we're moving on to start talking about connectedness as a computational property and problem. Right, so we've seen all the previous graphs here are connected, but we've also seen examples of graphs which are not connected, like, let me show that, this one here, right? Not connected, we cannot get from here to here, nor to here. And so how about as an algorithmic problem, given a graph as input, can we find out whether this graph is connected or not? Whether it's possible to get from any vertex, start vertex, to any target vertex at all. And let's consider two versions of this problem. The first problem we're in is called ST connectivity, from source to target, from start to end. So in this problem, we're really first interested in, given two vertices, is there a path from start to end vertex? And to this end, we first need to specify how the graph is given to our algorithm. And as I said, one of the several ways of encoding a graph is by using the adjacency matrix. Here we consider the adjacency matrices with value 0 and infinity. You can also say value 0 and value 1, where infinity means here no edge, and 0 means an edge is present. And also we put a 0 at the diagonal to indicate the absence of a loop. And then the question is, given such a graph and given two vertices of that graph, S and T's, source and target, start and end, is there a path from S to T in the graph? And there are two variants of that problem. First, if the graph is directed, and the second variant in the case the graph is undirected. Good, so that's a classical decision problem. Input is a graph, and input are two vertices of that graph that are input, and they are now fixed. Is there a path from this specific vertex to this specific vertex? And the algorithm for doing that, let's call that reachable. That is basically an instance of depth first search. You know depth first search, right? Algorithm implementable, for example, using a queue. And so for each vertex in the graph, we first mark that initially as unvisited yet. And then we execute depth first search on the graph. Depth first search or breadth first search, it doesn't matter. Just your ordinary graph traversal, recursive graph traversal algorithm with the goal of marking any vertex that has been visited and starting with a start vertex S. And so this algorithm, any graph traversal algorithm, depth first search, breadth first search, in this way, executed in this way, will mark all vertices that have been visited and therefore all vertices that can be visited. So that in the end, after the execution of this graph traversal, we can just look at the target at the end vertex, whether it has been marked to see whether it can be visited or not. So that's the first algorithm for the so-called directed and undirected ST connectivity problem. Let's briefly take the time to analyze the computational cost of that algorithm, shall we? So the initial phase is to mark all vertices as unvisited. That is linear time, right? Every vertex is visited or marked as unvisited precisely once. And if we have n vertices, that means that loop gets executed n times. And then there's a graph traversal, and again, a graph traversal visits every vertex at most once. Only the vertices that can be reached, of course. And each vertex is visited at most once, so that if we have n vertices, also the graph traversal incurs a computational cost linear in n, so that the total running time of that algorithm is linear in the number of vertices of n, and particularly it's an efficient algorithm. It's a polynomial time algorithm according to our classification. Let me emphasize that improving the computational cost of this problem has been a major source of research. And when I say improving the computational cost, I don't mean in terms of time complexity. Running time O of n is, of course, the best we can achieve and hope for, right? But the question is, how about the memory use, right? So how much memory does a graph traversal use? And can we find more memory efficient algorithm? I won't go into the detail. That's a subject of a different course of computational complexity, and in particular memory complexity. And there have been in 2008 some tremendous and I'm going to say surprising breakthroughs on this problem. But for now, let's return to our more basic introduction to algorithm. And since time is running out, let me stop here and recap so far and point out where we resume on Thursday. So we've been talking about graph properties, about quantitative and qualitative properties of graph, about types of graphs. Quantitative properties include the degree of a vertex, the maximum degree of a graph, the diameter of a graph. Qualitative properties include whether the graph is directed or undirected, whether the graph is connected or not, strongly connected or not in the case of directed graphs. And then we talked about regularity of a graph, diameter and degree, and the trade-off. And finally, we started discussing algorithms for checking these properties of graphs. And this is where we're going to continue on Thursday. And Thursday we'll discuss the all shortest path problem, not just one path from S to T, but the shortest path, and furthermore, shortest path between all pairs of vertices. So that's all for today. Thank you very much for your attention and see you on Thursday.